Okay, this is module 12, use properties of tangents. In the following few modules, we're going to be talking about circles. And my advice to you is to get between 5 and 7 colors of colored pencils or markers to use on your notes. It will help color coding when you actually look back and do some of the examples. So, first thing I have to do is I have to define what a circle is. And a circle is a set of points in a plane, so a two-dimensional surface, that are equidistant from a given point. So I have the given point is called the center, and I have it labeled in blue. So there's my blue, there's my center. The next thing I have to define is something called the radius. So the radius is a distance from the center, from the blue, to the point on the circle. So it's a segment, it's an actual line segment, whose endpoints are the center of the circle and the edge of the circle. So I color code that with red, so you can see. Two circles, we say they are congruent if they have the same radius. Diameter, that's the distance across the circle through its center. So what I did is I did this in another blue, a darker blue. So darker blue, that's my diameter, and I have my diameter in the figure as well. So the diameter, again, is the distance across the circle through its center, and we label it as a chord that passes through the center of the circle. And we'll define what a chord is in a few seconds. So here's what a chord is, and I used yellow for this, again, to color code, just so I can easily look back in my notes and see what's what. So a chord is a segment whose endpoints are on the circle. The diameter is a special type of chord, so we call it a diameter because it actually goes through the center. But again, if it doesn't go through the center, we would just call it a chord because it's a segment whose endpoints are on the circle. A secant. This is something you're going to be referring to a lot in higher level mathematics, namely calculus. So I labeled this with a green. And what a secant line is a line that intersects a circle in 2 points. So I have my 2 points here, 1 and 2. And the difference between a secant and a chord is a secant is a line. A chord is a segment. And then last, we have a tangent. And a tangent is a line in a plane of a circle that intersects the circle in exactly 1 point. So I did this in purple. So there's my 1 point where it intersects the circle, and it does not intersect in any other place. And we call that a tangent, or a tangent line. Okay, so in this figure, I want you to pause the video and see if you can identify, using the proper notation, the center, a secant line, a tangent line segment, a diameter, a radius, and a chord. Please pause the video now and try and see if you can do that. Okay, you can check and see if your answers are correct. There are a couple multiple answers for a few of these, but center I labeled as C. Secant line, it's AB, so we have the 2 points A and B, and remember you have to have the notation of the line on top of it, on top of the 2 letters. We have tangent line segment, which is H, that's labeled here. We have the diameter FE, or EF, it does not matter. We have a radius, there's multiple different ones, I just picked CD, because that's one. And we have a chord, AB, or we could have FE. And again, segment on top of it. For each one of the radii, the diameter, and the chord, you have to have the segment notation, and for the secant line, you have to have the line notation. Okay, so a few theorems that are associated with this. We have 10.1. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoints on the circle. So what does that mean? So if I have a circle that originates from center Q, so here's my center Q. So line M, we would say, is tangent to circle with center Q. This is the notation that states circle with center Q. If and only if line M is perpendicular to QP's segment. So we have QP's segment here in red. That's QP's segment. We have line M, that's this line here. It's tangent and we have a radius drawn to the point of tangency, that means that these two lines, line segment and line, are going to create a 90-degree angle when this occurs. So that's your first theorem. Theorem 10.2 says if two segments from the same exterior point are tangent to a circle, then they're going to be congruent. So in this case, if I have a circle and they originate from the same exterior point, for example, I've got an exterior point S, and I draw to a tangent point R, so here, and I do the exact same thing but on the other side, and I have another tangent point T, that means that SR is going to be congruent to ST. And it doesn't really matter where the exterior point occurs. It can occur further in, or it could occur outside. It doesn't matter. So either or, this basically works. Think of it kind of like scissors that are going across a CD. So, but again, if we have two lines that are tangent and they originate from the same point, that means the segments created are going to be congruent. Okay, so we're going to apply some of these things. And a lot of this because of right angles that are created with the theorem. So here are your theorem 10.1 examples. We're going to be using Pythagorean theorem. So in the first one, what I have here is I have a radius drawn from point C to point B. And then I have a tangent segment that's created here with AB, which creates a 90-degree angle. So if that's the case, if I draw this part here, I'm trying to solve for x. Okay, so try and solve for x, which means I'm going to use the Pythagorean theorem. We have x squared plus 32 squared equals the entire length of the hypotenuse, and that is going to be x plus 16. You're going to have to go back to algebra, in which case you're going to have to FOIL this part here, or double distribute. So in this case, I'm going to do x squared plus 1024 equals, if you want to write it above here, x plus 16 times x plus 16. First, outside, inside, last. So we have x squared plus 32x plus 256. And you solve. The nice thing about this is the x squareds cancel out. So once we have this, we subtract 256. We got 768 equals 32x. Divide, we get x equals 24. So that's my value of x. Okay, so go ahead and try using this method for the second one. You can pause the video now and see if you got it right. Okay, so for the swimming pool one, you are standing 36 feet from a circular swimming pool. The distance from you to a point of tangency on the pool is 48 feet as shown. What is the radius of the swimming pool? So we're trying to find the radius. We set it up the exact same way. We do r squared plus 48 squared equals the entire length of the hypotenuse, which is r plus 36 squared. I didn't do the actual algebra because I have an example that's right next to it that's very similar to it. So you can see if you did it correctly. If you didn't, you might have made an algebraic mistake. Okay, and theorem 10.2 examples. I tell you in the directions that JK is tangent to circle center L. Again, that's what this notation says. Circle with center L at K. And JM is tangent to circle with center L at point M. So that means they originate from the same point, the exterior point. So what I'm trying to find is I'm trying to find the value of x. So I'm going to do the first one, and if that's the case, that means they originate from the same point to a point of tangency. That means the segments are going to be congruent. So that means 4x plus 7 equals 7x minus 8. When you solve, you get 15 equals 3x, and then you get x equals 5. And we're done. So use that as an example to try and solve for x in number 2. And if you do it correctly, you should get x is equal to 2.